Hello, everyone, and welcome to another episode of The Raw Men. This time I'm talking with paleontologist Viktor Radermacher and Dr. Bruce Rubidge. These are Rubidge from the University of Witwatersrand, or Witwatersrand. I think it's about the best I'm going to be able to do with that, in Johannesburg, and also a geochronologist, Dr. Jahan Ramezani from MIT. And we're talking about paleo expeditions in South Africa. So, is it Rubidge?
Rubidge is the correct pronunciation.
It
Yes,
is.
Aaron.
Okay. Very
Thank
good.
you.
So, what is it that your group has done or is doing that would be good to talk about?
Aaron, what we are wanting to do is we are doing some exploration, field exploration, to find the oldest therapsid mammal-like reptiles possibly in the world, and we've been wanting to do that in South Africa. South Africa's Karoo supergroup has got some of the richest deposits, in fact, the richest deposit of mammal-like reptiles, therapsid mammal-like reptiles in the world. And so we have launched a crowdfunding exercise, which we would like to make people aware of, and if people feel they like it, to subscribe to that, because we are finding that we're having funding limitations, and I would like to launch an expedition to South Africa next year. Now, the area that we're wanting to work in is in the Karoo in South Africa. And Victor, if you can get me that picture up, where we have remarkable outcrops of rocks, and they cover a very long time period. So the map that you see in front of you here is the Karoo supergroup. It covers most of South Africa, that area that's dark brown and light brown and into the green. And it covers in the oldest rocks that are 300 million years old, and in the youngest rocks on the top, the purple rocks, 180 million years. So it covers a period of 120 million years, which is the time that reptiles appeared on Earth and radiated into different directions. One line giving rise to tortoises, one line giving rise to dinosaurs, crocodiles, and birds, and another line giving rise to mammals. And it's the line that gave rise to mammals, the animals called therapsids, that particularly are exciting to us, because the Karoo is very rich in those fossils. And if we can just look at the next slide, these are the rock outcrops that we look for these fossils in the Karoo. And this rock outcrop that you can see in front of you has different biozones in it, as I'll explain in the next picture. So these different colors that you see here are different zones of fossils that particularly set up on therapsids, because they're the most plentiful fossils. And what we are wanting to look at is the yellow zones at the bottom here. Those cover a period from about 267 million to 260 million years ago, when the earliest therapsids lived in the world. And what is exciting about them, in that whole yellow area, we've collected various intervals around them. And that's why Jahan has come on also, is because he looks at the volcanic ashes and is able to date the volcanic ashes that come out of these layers. So we're looking at biodiversity change that occurs in this time period from 267 to 260 million years ago. And at the end of that period, we've identified a massive extinction. In fact, about an 80% extinction of land-living animals. And a similar extinction, it's the end Middle Permian or end Guadalupean extinction, has been picked up in the marine realm in China. But South Africa has got really the only record of that extinction event on land in South Africa. And the dates that we have of that are 260 million years. So it links in with the extinction event in China. And this is why we are excited by this project, because we are making groundbreaking discoveries. We're discovering new species. It is also the earliest terrestrial environment in South Africa, because prior to the 267 million years, the Karoo was covered by a sea, and then we got land beginning to develop as deltas exposed the shoreline, and as soon as we get a shoreline, we start finding fossils of reptiles living on that. And we've just returned now from a field trip to the lowermost Karoo, the earliest terrestrial deposits, and we found 2 new species of animals that have never been discovered before. And so this is particularly exciting to us, and why we're wanting to explore these layers further.
Give me an idea what the 2 animals are, first off. Hello?
Sorry. Hi. Sorry. I got interrupted.
Can you give me a description of the 2 animals that you discovered on your last expedition?
Yes, Victor, there's some pictures there. If you can just show us. On the screen here is a very nice large skeleton. You could see it's about 3.5 meters long of a Dinocephalian. Now, Dinocephalians were very large mammal-like reptiles. In fact, they were the first really large animals to live on land. And this skeleton that you see on the screen is particularly well preserved Dinocephalian. In fact, it's the best preserved Dinocephalian skeleton yet known. And Dinocephalians are known from South Africa. They're known from various African countries, but particularly from Russia and Brazil and China. But the South African Dinocephalians are some of the earliest in the world. And this one, which is a new species called Tapinocaninus, it took 25 years to expose it from the rock. It's been a hell of a task to get it out. But we've now just recently, last month, published a paper on the skeleton of this animal and been able to give an indication of what this animal would have looked like once upon a time. And so these are the largest animals that lived, but most of them were smaller, dicynodonts with a skull about 15 centimeters long, a thing called Eodicynodon. And then we also find the large animals called paraiosaurs, which of the oldest ones are found in South Africa, but they've got more recent ones that occur in Russia, in South America, China, and also in African countries such as Zambia, Zimbabwe, and into Niger as well.
Now, I was aware that the paraiosaurs are quite large, but I mean, apart from like Scutosaurus or whatever, this thing here, when I first saw it, I was like, that's quite big for that time period, because I don't remember much of anything being that big in that time period.
Yes, you're right. And this animal would have weighed more than a ton. Our recent work shows that. And so this is a particularly large animal. It had a semi-sprawled front leg gait or stance, if I can put it that way, and the back legs were tucked in under the body. So it was beginning to move from a sort of, call it a typical reptilian stance, through to a mammalian stance and a mammalian gait. But Dinocephalians, the problem with them is their taxonomy is not well sorted out. South Africa has the richest record of Dinocephalians. We find both flesh-eating and plant-eating forms, but the plant-eating forms, which are quite diverse in species, are in taxonomic disarray. And so I've got a student currently working on that, and hopefully we'll come up with new ideas on the taxonomy of Dinocephalians and then be able to link them with similar faunas from other parts of the world as well.
So I'm gonna talk about a little bit of a paleo controversy. Here in the States, paleontologists would not, or people who teach evolution, and especially in the scientific community, would not ever refer to themselves as Darwinists. While some people in England, for example, Richard Dawkins doesn't have a problem, referring to himself as a Darwinist, and that just irritates us over here in the States. I did an interview with another paleontologist, Don Prothero, recently, who wanted to make sure that we never ever use the word mammal-like reptiles. They are not reptiles.
So all my American colleagues tell me that I mustn't use that term. It's a term that's generally used by the public in South Africa, but my American colleagues tell me I must use the term therapsid. So maybe for the rest of this talk, we'll use the term therapsid.
Yeah, and so that's not the extent of paleo controversies, but that's the more burning ones. Okay,
I think that's one of the exciting things of the South African record, as you well know, is that because these rocks extend over such a long time period, and because they're rich in fossils of therapsids, we can look at the changes in those therapsids from the oldest forms, 267 million years ago, to the youngest forms, to 180 million years, when we actually have the earliest mammals in the world, appearing in the Karoo at about 200 million years. So you can see the changes in morphology that have taken place. And with the work that we've been doing with Jahan on dating these rocks, we can now actually put time ranges and times onto how long it takes for morphological features to appear and to evolve in these mammal-like reptiles.
Well, then that would be a good time for me to interject. I mean, you were just showing a geologic map, which doesn't seem to imply a global flood at all, but yeah, and of course, what I normally deal with in my activism is a lot of young Earth creationists who just have no idea how to interpret a geologic map, especially when you take them out to the field to show them, and then they go through the denial process. But when you say that you have somebody that's ascribing dates to these, one of the arguments that I often hear is that that people date the relative dating, dating the layers by the fossils that you typically find in them, and then you somehow ascribe an age to that, also by the circular reasoning of dating the layer by the fossils and the fossils by the layers and so forth. And I have to point out that no, we use radiometric dating for that. And then the argument is, well, radiometric dating, they only think that there's carbon dating first off, and that's the only, which of course is never used in paleontology, but that's the only one they know about. That's the only one they will admit. So, Dr. Jahan, you there?
Yes, I'm there. I'm here. Yeah.
I would like to hear from you how you deal with people that do the young Earth creationism argument and argue that there's no radiometric dating. And I don't want to make this discussion about that, but I know that you have information that would be helpful on that. So if we could just take a minute to hear what you have to say about that.
We have many different methods. Well, actually, the right term is radioisotopic dating. So we have different radioactive elements with different half-lives that have application for geochronology, for radioisotopic dating in geosciences. And for example, carbon dating is one of them. But there are other elements, there are other radioactive isotopes like uranium, like potassium, and these have much longer half-lives, and we can use those for dating much older events. For example, the kind of events that we are talking about right now, the rise of mammal-like reptiles in the Permian in the 260-something million years. And with these tools, with these radioactive elements with long half-lives, we can go back all the way to the origin of Earth and the origin of solar system and measure geologic or planetary materials. So we are not stuck with one radioisotopic dating technique and a very limited range. So depending on what problems we are trying to address, we have different tools in our toolbox, different elements, different isotopic systems, and each of them have their own applications. And so that's one issue, and something that I think is relevant to this discussion, your audience should be aware of, is that the geologic time scale, for example, when we're talking about Permian, we're talking about Triassic, Jurassic, Cretaceous, these are defined originally not based on radioisotopic dates. These are originally defined based on marine fossils, based on creatures that lived in the ocean, and when they appear and when they disappear from the geologic record. So radioisotopic dating is a later contribution, basically, to geologic time scale. So now we are able to go back and put absolute numbers on those geologic boundaries, time scale boundaries. So that's something to remember. I think did I answer your question, or is there something else you wanted to?
Oh yeah, there's definitely something else. We were talking before we started recording about how I often hear the complaint that radiometric dating doesn't work. Excuse me, radioisotopic dating doesn't work because it's based on assumptions or whatever. And it's people that don't understand it. Now I can simplify an explanation of how radioisotopic dating works, but I don't actually do it firsthand. So I'm just a guy, right? So you're the PhD from MIT. You're the one that does this for a living. I mean, you have hands-on personal experience with this.
Sure.
So if you would please, I would love to hear you explain, how radioisotopic dating really does work, and no, it's not based on, some erroneous assumption.
Sure. Well, the basic principle of radioisotopic dating is a radioactive decay. So this is like how fast these elements that are unstable, and they break apart and they turn into other elements, like uranium turns into lead. So the basic principle is the radioactive decay, and radioactive decay is a physical constant. So it's one of the basic constants in the science of physics. So it's like a speed of light. So we know exactly, we have been able to measure, scientists, physicists, and especially nuclear physicists have been able to precisely measure how fast these elements decay, these radioactive elements decay. And the fact is, this decay, because it's a nuclear process, it's related to the nucleus of the atoms, not the electron shell of the atoms. These are constants that are unchangeable. So it doesn't matter if you take a uranium, take a few atoms of uranium, you melt them, or you precipitate them from a solution, or you combine them with some other compound. That radioactive decay, that rate of decay does not change, because it is shielded. The nucleus of the atom is shielded by the electron shell. So what happens to the atom? It involves electrons, but it doesn't involve the core, the nucleus of the atom. So that's something that everybody should remember. If you believe in physics, you believe in principles of basic physics. This is a constant. We have many different physical constants, and radioactive decay is one of them. So each radioactive element has its own decay constant, or half-life, if you say that it's unchangeable. There's no natural process that can change the rate of radioactive decay. So that's one thing.
I want to jump in with one of the things that the people who don't understand science, and very often here in the States, it's people who don't want to understand science. One of the complaints that they would make, or they would say that you don't know how many or how much of that had already been decayed before you found it. You don't know what the original is. And so I understand that anytime you study anything in depth, it's going to become more complex, and you're going to find exceptions or variables, or how to account for these various things. So how would you explain that aspect of it?
Okay, so the second big assumption that goes into radioisotope dating is that radioactive material element was incorporated in the material that we are measuring, we are analyzing, and that material, that mineral, that rock, stayed as a closed system. So there's no parent radioactive element introduced or left the system, and also no daughter products, no radioactive products entered or left the system. So this is a really important thing for us. So we go to real distance to verify that a system that we're working on, the material we're working on, remained as a closed system, and it was not disturbed. It's not isotopically disturbed throughout those millions of years that those rocks have been sitting around. And we have all kinds of tests that we can employ to be sure that that assumption of the closed system is valid. So one of the simplest things is that, for example, we are working on ash beds, we are dating volcanic ash in the Karoo Basin. So we have a stratigraphy. So we have a succession of rocks, and we know for sure that the rocks that are in the bottom are always older than the rocks that are on the top. right? So that's very
I've
simple.
actually heard people argue that it's possible to get that the other way around, and I've
It
never
is
heard an
possible.
explanation of how that could possibly happen. No, the rocks below are going to be older. There's just no way to insert another layer under that top one.
No, it's not. And to anyone with a really basic geologic knowledge, at a bachelor's level, it's quite easy to figure out what if it's a normal stratigraphy versus reverse stratigraphy. If you're looking at a limb of a fold, for example, that's overturned, so things are in the reverse order at the surface. So no, that's not a big problem. So this kind of test of superposition is something that we can employ when we date ash beds that are lower in the stratigraphy compared to the ones that are higher in stratigraphy, and we get the right order. The ones in the bottom are always coming out older than the ones on the top. That's a test.
Well,
that's a test of the validity of our dates.
Another thing I want people to understand is that I've heard many times people argue that you can't date fossils, and that's true. You can't date fossils, but like the Devonian strata, for example. I mean, it was named after the fossils that were found in Devonshire. That's where they get Devonshire, England, so that's where we get the name of this strata. But that strata is identified by those fossils and its position in the geologic column all the way around the world, which a lot of people don't understand. So the Devonian strata exists in Devonshire, and it exists everywhere else in the world. It's just where you find it. And then how do you get an age on that? If you can't date the fossils, but you can date, as you said in this formation, you have, did I understand you to say that you have magma intrusions, that you have like
volcanic ash? So the idea is while these sediments were being deposited and while these fossils were being preserved, there was volcanic eruptions going on throughout the geologic history, going back to the very origin of the Earth. These volcanic eruptions produce ash, like the volcanic ash we see today in various parts of the world. And this ash gets deposited in between layers of sediments, sometimes directly underlying or overlying the fossils that people like Bruce are studying. So those volcanic ash beds contain minerals that are very uranium rich. They're magmatic minerals. They form out of a magma, molten rock. And when they crystallize out of a melt, they basically suck up all the uranium that's present in the environment, in the magma. They concentrate it in the crystal structure. And they're extremely sturdy minerals. They're very resistant to physical and chemical change. So they basically work like little isotopic clocks. When they crystallize, they entrap the uranium in them. They don't let it go out. They don't let anything else come in, and then the chronometer starts to tick, and that uranium starts to decay over time. So what we do in collaboration with our colleagues, our paleontologist colleagues, is going to the field and collect those layers of ash bed. We sample them. We bring them to the lab. We do mineral separation. We separate those minerals of interest. The most popular one is zirconium silicate, which is actually a gem. It's used as a gem, and it's a common rock-forming mineral as a minor rock-forming mineral in many magmatic rocks, including granites, including lavas, including volcanic ash. So I can show you a little kind of PowerPoint that tells you how this process works. If I can get it to start.
Okay, I see it.
You can see it?
Yes.
Okay, so that's an example of volcanic eruption today, present day volcanic eruption. And this is a layer of volcanic ash that you can see in between sediments. So the rock hammer is sitting on a layer of volcanic ash that stands out very well relative to the sedimentary rocks. And these are crystals of zircon, zirconium silicate, that we separate from that volcanic ash. There's a scale bar up there. It's 200 micron. It's 0.2 millimeters. And it tells you how small they are. They're microscopic. And then we collect those, and we basically analyze those in the lab. I can show you a very kind of a simplified schematic. Again, those are multiple zircon crystals, and we take individual. We have our technique has improved to a level that we can take individual microscopic crystals of zircon, and we can put them in the capsules in the lab, and we can add an isotopic tracer to it. This is a solution that contains uranium and lead of known isotopic concentration and known composition, isotopic composition. And then we can dissolve this whole thing in hydrofluoric acid. It requires really high temperature, high pressure in high pressure vessels in the oven to actually allow the hydrofluoric acid to attack zircon, dissolve it. So the solution that comes out from dissolving zircon goes into chemistry columns in a clean lab environment, which is free of metallic elements, free of metals. It has to be very clean because we work with very, very small quantities of uranium and lead at the picogram level. Picogram is 10 to the minus 12 gram. So it has to be extremely clean and a metal-free environment to do this process. And then through these chemical processes, we purify and we separate uranium and lead, and we put them as a little drop on these mass spectrometer filaments. And these go inside a thermal ionization mass spectrometer, where we can measure the isotopic compositions of uranium and lead. And this way, we can actually calculate how much of the original uranium in the mineral, in the crystal, has decayed over time to daughter lead isotopes. And by doing this, and by knowing the, should I put this out of sharing? Yes. By knowing the decay constant, the half-life of uranium, we can actually solve the equation for time, measure the time. So that's basically how the process, simply speaking, how the process works.
I appreciate you making that a simple explanation. For those who don't think it was a simple explanation, I had a talk with Benjamin Berger, who's a paleontologist out of Utah, and his explanation of how he did radioisotopic dating was not simple at all. It went on for 45 minutes. It was completely over my head the entire time, and this is something I'm interested in, yet I was completely lost listening to him. And it's happened very often that he's gone over my head, and I'm like Ben.
So I hope I could clarify for you to some extent. I'm happy to explain it more if there's anything.
Well, there's one thing that is important for people to understand if they don't understand radiometric dating. It's like, okay, so you have these ash fields in this particular strata in this particular location, but then we have other type of magma intrusions in other strata and in the same strata, and they're all over the world. So when you date any one of them, let's say if you didn't have any dates for anything, if you date this strata, would that not imply that this particular formation, the Karoo, was the age that was given, and so everything that's above that has to be younger, and everything below that has to be older. But then you have all of these other dates for all of these other magma intrusions for all of these other locations all around the world, and they're all coordinating with each other. They're all giving similar ranges.
Exactly.
So that we actually do know for certain that these are the ages that we're really getting, because we're not even just using the uranium to lead, I believe is your specialty.
Mm-hmm.
But we have like what, dozens, literally dozens of other radioisotopic dating methods, as well as, some additional ones with VARs and
we have
counting isomers and so
argon
forth.
dating, which is overlaps with uranium lead dating.
And while everything has a range of, accurate up to, say, give or take 1,000 years either way, it's going to be so many millions of years. Like I think the latest dating on the KT iridium layer was 66,038,000 years, give or take 11,000 years either way. And people will say, "Well, that's heavily out. You don't know. No, it could be 11,000 years this way." Wait, it's still going to be 66 million years. We got
There's a really small error bars on the other side of 66 million.
It is a scientific work, and we report our uncertainties. There are anything that we measure in science has got uncertainties, and we try to quantify that uncertainty and report it. So all of the ages that you see coming out of our works has got they have got error bars associated with them that tells you exactly what is the uncertainty.
But even understanding that there are some variable ranges of uncertainty, when you take everything together, when you take all these different types of data, when you take all the different locations and all of the consistency, time and again, at all these different layers everywhere around the world, we're coming up with one answer, and everything is coordinating. Give or take 11,000 years this or way there that, but every layer has the same coordination. So there's just no. I mean, it's not a guess. It's there's something that we actually know, and this was something that I wanted to explain to people in my audience, or to like the creationist apologists that wanted to get in there. And now we're done with that. I want to thank you very much for that explanation. And
if I can just come in, Aaron.
Yes.
If I can just come in, I think that the exciting part of this work that we're doing with Jahan is that we send him blind ashes. He doesn't know where they come from, and he gives me a date back. And all the dates that he sent back to us have come in the right order, with the oldest at the bottom of the mountain and the youngest at the top of the mountain. And we've done this over several years. So this has been really exciting. And we're now able to look at exactly when certain species appeared first in the rock record and when they disappeared. And that gives us a time, an indication of how long species evolved, times of extinction events. And I think that for the Middle Permian, this is groundbreaking work that we're achieving in South Africa.
And the Permian is actually my favorite period of paleo history. I mean, there's no dinosaurs, and so why would I be interested? No pterosaurs, but it is, as you put it, the therapsids, the diversity that we have in what we would call proto-mammal-like creatures. I mean, things that aren't yet mammal, but you can tell that this is where they're going to be. There's such a range of diversity of different types. I mean, filling every niche that we have today, like gopher types and hippo types, but of course they're not gophers or hippos. And that world seems to me to be so much more alien than the typical jungle dinosaur environment that we see in all these movies. The Permian seems to be very weird.
Well, I think it's weird because people don't understand it yet. There's so much there that is not being given the popularity of dinosaurs, and so it's up to us now to do something about that. And that's what I've been trying to do in my life, and I will continue to do, to try and popularize these animals, because they are our ancestors. They are our ancestors of 260 million years ago. 260 million years ago, there were no mammals yet on Earth. Those were the closest forms to modern furry animals. And at that stage, their bodies were probably covered with scales, and gradually through time, their bodies became covered with hair. And it appears that happened probably about 246 million years ago. Again, these are sort of ages that we get out of the rocks from people like Jahan, who are giving us those ages for those rocks, and then we look which fossils occur in those layers, and we're able to date the fossils in that way. And so all of this evidence is coming together in the right sort of way now, that we are able to look at how old the animals are, and then we look at their morphological characteristics, and we start seeing things that are the characteristics that they're starting to develop. And I think that a field that one of my colleagues, Julian Benoit, is working on is neuroanatomy. He's looking at how nerves and blood vessels innervate various parts of the snouts, because he's found that certain nerves innervate certain tactile hairs, like whiskers. And so he's looking at when those nerves appeared in the fossil record, and can
so
pick
the
them up,
nerves-
because we've got scanning techniques now that enable us to look right inside the skulls. CT scanning enables us, and that's revolutionized our science in the last decade or so, because now we can look in places that we've never been able to get before, into skulls.
Yeah, I wanted to ask you about that too. I knew that there was, because of the nerves that you're talking about, that there was indications of whiskers in theriodonts, for example. But
Yeah.
we don't have actual proof of fur until until like we have like coprolites for cynodonts. Is the first. But I want to hear from you, from your experience. How do you think the emergence of hair happened? Did it start with whiskers, or was it, or did it have hair anyway and then became sensitized?
Let me try and field this question. So it really depends which side you look at it. You know, it can almost be a chicken and egg scenario. Our body hairs secondarily modified whiskers, or whiskers secondarily modified body hairs? And you know, depending on what your hypothesis for that is, will determine what these things will look like. One of the weird things about the Karoo Basin is that we have thousands upon thousands of fossils, and we actually have very few skin impressions. As when you compare it to the dinosaur record. And what that suggests is that these things didn't have necessarily hard scales like squamates did, but they might have had leathery skin. And if they did have hair, it probably didn't preserve. But what we can do is like look at this trigeminal nerve and look at this proxy for whiskers in the fossils. And we can anticipate if whiskers evolve in eutheriodonts, that means that the precursor to whiskers would have been in theriodonts. So whether or not Gorgonopsids had fuzz, it's still, the jury is still out on that. But things like cynodonts really did evolve whiskers really early on in their evolution. And that probably led to their success, being able to function in day and night and exploit those niches when other animals couldn't either.
Yeah, well, we don't want theriodonts to have fur, because that makes them lovable, and they're
I like my Gorgonopsids naked and badass. I don't like the idea of fuzzy gorgons. That's a little gross to say.
Yeah,
but Aaron, I think that's one of the exciting things that we are beginning to look at now. Because of scanning techniques, we can now look inside burrow structures of these animals. And as you know, a burrow is a hole in the ground. And if you want to preserve a burrow, you need to fill that hole. And so with sediment filling these burrows and trapping animals inside them, we actually find these vertebrate animals, like these very early mammal-like reptiles, preserved in the burrows. And we've launched a project over here a couple of years ago to try and look in different burrows, scanning them, and to seeing what the animals are doing inside there, because we were hoping to find maybe traces of hair, traces of eggs, those sorts of things, maybe traces of live birth. We haven't answered any of those questions yet, but we're obviously looking in the wrong burrows. And I'm sure that with looking in more burrows, we will come up with those answers, because we are continuously finding new answers to questions that we pose. The fact is that the whole Karoo is so full of fossils. As I said to you earlier, I've just come back from a 2-week field trip, and on one day we catalogued 95 skulls of early dicynodonts from one locality. They're just amazing, the number of things that come up. Where I'm wanting to work is a little bit more scarce. The animals, we probably find 4 animals a week. But then the chances are, because nobody else has explored those layers before, the chances are that there'll be something that other people haven't seen yet. And as I said to you earlier, because of this field trip that we've just done, we found 2 new species of animals in 2 weeks, which was really quite exciting for us. So there are new answers coming up all the time. Every time we go out, every time we explore, we find new stuff. And I think that's the exciting part of the type of work that we're trying to involve ourselves in South Africa.
No, I'm interested.
There's one over here that we can show you if you'd like.
What's that?
Yeah, bring that one.
Yeah. So there's a new Gorgon found.
And for those who don't know, the Gorgon that he's talking about, we're talking about the Gorgonopsid, right? There's the Theriodonts.
Yeah, Gorgonopsids, yeah.
The size of a large dog to the size of a grizzly, and saber-toothed sort of quasi-dog lizards.
Yeah. I call them reptilian wolves.
Yeah. Now, you could see over here, Aaron, there's a tusk coming out. I don't know if you see it.
I do see it.
This is the fossil that we found 2 weeks ago. So there's a tusk coming out here. There are a whole lot of teeth exposed over here. We haven't done much to this yet. We're still going to open it up. But there's the eye. Can you hold the rest of it? Okay. Yeah. There's the eye over here and the back of the skull over there. Now, this is a particularly large Gorgonopsian for this time period. We haven't found them this size yet. And this makes this a very exciting specimen to work on.
Yeah, the bite that thing must have.
Well, let me show you something really cool. Is that we've actually prepared some of the teeth just today, actually, and you can see that this is one of the canines that is descended out of the maxilla, and you can see some of these, what we would have called incisoriform, pre-canine teeth, and yeah, they have been described as having something called a malleognathic jaw condition, which just means hammer jaw. So they've got these really big anteriorly heavy lower jaws. I just would have slammed into prey, just totally obliterating them with these really fantastic teeth.
So you can't make something like that fluffy, because that's just a super monster.
You see what I'm saying? Exactly. You gotta make it like cool and leathery. Yeah.
So I think that's a really fearsome, with these large saber-toothed canines that it's got. It was a very fearsome predator. How fast it moved, I don't know. So I don't know if I'd lived at the same time as it, whether I would have been able to run away from it or not. It probably was able to, like modern cold-blooded animals, poikilothermic animals, probably could move quite fast when the sun was out. But I don't know what it was doing when the sun was down.
Yeah, the evolution of is homeothermy the right word? Yeah. So yeah, that one's another one that intrigues me, because how we warm our bodies, I thought, was that we had a constriction in the veins that caused the friction to warm the blood. But then I was corrected in saying no, it's actually the way we burn calories.
Well, constricting your veins is burning calories.
Thank you. I was told that it was a chemical heating, and I said no, it's a friction heating. But it was an argument that I would. And thank you for saving me out of that one. All right, so you guys are trying to fund an expedition into this Karoo formation, and there is a link included below, so that people can donate to that endeavor.
Yeah.
Is there anything you want to say about that?
Well, I think that it's probably one of the more exciting projects that's come up in the Karoo in recent years, because we've got a large diversity of fauna already discovered there from our work over the last 2 decades or so. And we're now beginning to see the gaps. And so we're targeting those gaps and going in to look at who occurs in those intervals that we haven't found things in. And with our dates that and good dates that we're getting right now, we're able to then put ages onto these gaps that we are identifying and filling with more work. And so I think that's an exciting project. South Africa has got 200 meters, that's 2 kilometers of rocks, sediment that was deposited in the Middle Permian period. It's the richest and the thickest Middle Permian deposits in the world. And so if we're going to find answers as to how our distant therapsid ancestors evolved and when they appeared on Earth, and we're going to find it in the Karoo. And the important part is, because it's such a complete sequence in the Karoo, and we find bits and pieces of that sequence in other Gondwanan countries and Pangean countries, the Karoo story is really like the complete jigsaw, and the rest of the world needs to fit into that jigsaw. And so this is providing the total picture for the jigsaw, and hopefully we can then use that to sort out the problem in other continents in the world.
The really unique thing about the Karoo Basin in particular is that it's originally was a bowl-shaped landmass, and because of that, we have a virtually uninterrupted sequence of rocks. And within those rocks, we have really interesting stories about the development of life. Everything that, people like saying that the Triassic is weird and the Mesozoic is weird, but all of those critters really have their origins in the Permian. And we'll be hitting the rocks of the right age, and with an uninterrupted story. We have a chapter in that story that is pretty unexplored. And what this experiment project hopes to do is to really fund research to that missing chapter, to try and find texts that will help answer these interesting questions. But then secondly, the really important work that Johan's doing as well is that we can now not only calibrate these events, but we can also start looking at the evolutionary rates of these events. How quickly did endothermy evolve? How quickly did did hair evolve, for instance? When did parental care really kick in synapsids? All of these sorts of really interesting questions come from working hand in hand with geochronologists and just doing hard field work and finding the right fossils. The rocks that we aim to explore are exactly that. It's a perfect overlap. So exactly the rocks of the right age.
Do you have an illustration of our closest known potential ancestor from this time period? Something that we can show on screen for people to have an idea. In the Permian, your great-great-grandfather looked like this.
Well, it would have... Well, our greatest. Well, okay. I actually have. So there was an article published pretty much an hour ago.
Well, that's timely.
Exactly, on the conversation about this exact skull that I showed you earlier. That was discovered by one of our other researchers. And in this article is one of my reconstructions of a Gorgonopsian, and I'm going to try and find that for you quickly. Let me just.
So this is not to say that this is our great-great-great-grandfather, but this is the closest relation we have from that time period.
Yeah.
Right?
So there are two Gorgonopsians going at each other, and you can see I've given them some nice leathery skin. And yes, so Gorgonopsians are like the perfect example to show people, because they really embody. When you look at them, you kind of have to ask yourself, is this a reptile or is it a mammal? It's got this reptilian gait to it in some ways, but then it's got these mammalian-like teeth and an overall doggishness to the face.
Yeah, and it has a reptile skeleton with lumbar ribs that, of course, mammals don't have. Doesn't have a diaphragm like mammals have. But then it seems to have had whiskers. So
Gorgonopsians probably didn't have whiskers, but the next clade up from Gorgonopsians, which is eutheriodonts, which is therocephalians and cynodonts, they likely had whiskers. Cynodonts definitely had whiskers, early cynodonts in particular.
All right, side question. Are there any eutheriodonts that really were venomous?
Oh, so you're talking about Euchambersia?
Apparently.
So is Euchambersia venomous? I mean, there's a lot of evidence to actually suggest that. It has all the markings of a venomous animal. It has this venom cavity in the maxilla. It has a little furrow in the canine to deliver said venom. But whether or not that deep fossa in the maxilla actually did house a venomous gland, or maybe some other sensory structure like pit vipers have. Vipers have these various pits on their face, and that's used for sensing infrared. No, I'm not at all suggesting that therocephalians were looking at infrared, but
that just makes them better monsters.
Well, of course, yeah. I prefer venomous therocephalian, but there are other alternatives that we are entertaining, and that we can. These are all hypotheses that we can really test by looking at modern analogs, and that is all work in progress. But of course, we need to increase our sample size for all of these questions, and you can only do that by doing field work.
As you know, Euchambersia comprises only two specimens. The one's in the Natural History Museum in London, and the other one is is here at the University of Witwatersrand. But those are the only two specimens, and they come from the Karoo. So the answers lie in the Karoo. We've just got to get out and do more field work.
All right. Well, I'm gonna share. As I said, there's the link to the fundraiser is below. and I will be sharing this video on social media and so forth. Is there any other things that did anybody want to throw anything else before we close this up?
If you don't mind, I chip in just for people who don't find Permian as interesting or exciting. It is a very important period of Earth history because the Earth is coming out of a major episode of glaciation, and it's heading towards the largest mass extinction that's recorded in the geologic history at the end of the Permian. So it's a very, very important time period of global climate change, and it's a lot of relevance to what we experience today, and in the in our environment. And we really like to know what was the interplay between life, evolution, and the environment and the climate. And we have tons of data from the marine environment, from fossils in the oceans, ocean chemistry, but there's so few studies that are done on the terrestrial Permian, how life evolved on the continents, how was the climate on the continents. So it's really a big hole in our knowledge of geologic history and animal land vertebrate evolution that requires a lot of work, a lot of additional work, more studies in places like Karoo.
The Permian is also important because it's a transitional period. I mean, it's still in the Paleozoic. We still have trilobites. We still have like orthocone ammonites and so forth. But we're also developing what people back in the day would say, dinosaurian looking kind of land animals, and so that this is the blend of the two eras.
Precisely, yes. And that extinction at the end basically turns the whole life upside down and eliminates a lot of fossils that we're creatures that we're talking about, opens up the room for new creatures and new life forms to come into existence. So it's really important. It's got real fundamental relevance to how life evolved throughout the Paleozoic and Cenozoic. I'm sure.
And I think from a vertebrate
more to it, yeah.
From a vertebrate point of view, it's the time that big radiation occurred from a very basal reptile-like form into therapsids, giving rise to mammals, into things like Unodontosaurus, giving rise to tortoises, and also things like Yangina, giving rise to ultimately dinosaurs and lizards and snakes and birds, I suppose, as well.
Yeah.
So it's I think a really exciting period and something that we know relatively little about.
Yeah, I'm going to have to put up illustrations of what the Permian period looked like, because to me, the reason I said earlier that it was weird was because the what we called trees for that period are not what we would recognize as trees now, and what we have left of those is barely grass. And
exactly.
And all these animals that you're talking about, they are traipsing about with Eurypterids, among other things that didn't exist in dinosaur time. Yeah, and some of them had crawled onto land, so we have Eurypterids on land now, and it just seems ghastly to me.
Well, one of the weird things for me is that if you time travel back into the Permian, you wouldn't hear any birds chirping, and I think we kind of take that little bit of ambience for granted. And you don't often pay attention to that, but I'm pretty sure you would notice it if it was missing. And there was nothing like that at all in the Permian. Animals were hearing in a very different way, so you might have heard completely different sounds as well. Like the mammalian ear hadn't developed yet, even.
So no music because
So
nobody
totally alien. Yeah.
All right, so I'm gonna close it up unless anybody has a final thought, and I want to thank you, all of you, for being on. This was very interesting. I don't know about anybody else, but I was very interested in the conversation. Hopefully, other people were too. Anything? I'm going to leave you guys to make the last comments.
Thanks, Aaron, and thanks for this opportunity. It's been wonderful to be able to share with people what the fossil record of the Karoo in South Africa means. And I think the exciting part is because there are deposits of the same time period in other parts of the world, we can use, as I said earlier, the total jigsaw model of the Karoo to understand what is happening in other Gondwanan countries at the same time.
All right, I'm close up.